beam before, right? We have drawn a cantilever beam before. And we have put a load P over here. And this is my point A, or this is our point B, and then at point C. And we know that failure will occur at point C, right? Now, somehow today, okay, before we have a break, this diagram over here, so this means it's equivalent to here. So if we have a cantilever beam, okay, let me specify the distance also. And we know that the distance from here to here, we know that the distance from here to here is L/2. And we know the distance from here to here is L/2. So somehow we have to prove, undo, that this is the same. What do I mean the same? So this is our point A. This is our point C. And then if we were to have an applied load going this way, this is P/2. And the distance from here to here is L/2, right? And the similarity is failure will also occur at point C, right? Now, this does not mean failure always at point C, okay? I just label it that way. Now, what you see at point C over here, we realize that X is not equal to 0 and Y is not equal to 0, but failure will occur at point C. On the other side, when it's a cantilever beam, right, X is equal to 0, Y is equal to 0. You can see that's what I was trying to tell you, right? Rather than looking at restriction of motion, we are going to prove why failure at point C and why a simply supported beam, okay, and a cantilever beam based on the load that you have seen, both are the same. And this can be proven mathematically. Okay. The thing about this topic, this course is this, okay? The physics and the math has to agree. If either one conflict with one another, there's something wrong. That's why I like to teach this topic. Okay, there is always a way to confirm your solution, whether is it right or wrong. Okay, some of you might call me crazy, but it is like this. Okay, so we know, right? We know over here that there's a reaction at point A. So AY, there's a reaction on the simply supported beam, and direction at BY. And we know that this is equal to P/2 because the load P is applied at the center, right? So some of you might think about this. We are analyzing point C. Why do we take P/2? Why we don't take the full P? Am I right? It ever come to your mind? It also come to my mind. Why is it we only look at, why is it that we only look at half of the structure? We don't look at both left and right. And the most interesting question, why a simply supported beam that you see on the left-hand side and the one on the right, why are they the same? So this is where we have to prove this mathematically. Okay. So what we are going to do now is we are going to derive the shear force and bending moment equations. Okay. So you have to see this mathematically, then you accept the fact. Okay, that's why mathematicians are all set bastards. Why do I say that? Unless it's proven mathematically to be correct, then they'll accept the fact. If not, they get real miserable. I'm the same. Okay, when I analyze a structure and mathematically it does not converge or it does not equate, that's where I have problem because each takes half the load. Yes, Katie, you are right, but I'm going to show you mathematically what is going on. Okay. So we're going to derive the shear force. Okay. So we're going to do 0x to L over 2. Okay. So this is where my datum is. Okay. At point A is where, so point A is the geometric datum. Okay. So, so that is where our geometric datum is. So we are now going to derive the shear force and bending moment diagram. Okay. So 0 to A. So we have a slider over here. So this is our variable x. And at point A, we know that there is a P over 2. Okay. Then we're going to have our shear force V as a function of x. And then we have a moment down here, M as the function of x. Okay. So some of you might ask me, Eugene, why that orientation? Okay. So let's recall why that orientation. Why V is coming down, MX is going anti-clockwise. Can you all remember? Yes or no? Anyone? And why? This is because we are assuming, we make assumption. Okay, why what I'm addressing now is why this direction. Okay, this direction is because we are assuming positive shear and positive bending moment. So what do we mean by that? Okay. So I will highlight this. What do we mean by assuming positive shear and positive bending moment? Okay. So when we carry out our analysis from left to right, so like for this case, we are starting from the left, we are going towards the right. So this is the analysis direction. Okay, so you can see from left to right. So when your analysis is from left to right, where we assume positive shear, your shear force will be coming down and your bending moment will be going in a anti-clockwise direction. So V over here denotes shear force, M denotes bending moment. Okay, so we are doing from left to right, and geometric datum is still on the left hand side. So this is our X. So this is our analysis direction. So as you can see, the shear force is coming down, the bending moment is going anti-clockwise. Now, I'm going to show you if the analysis go from right to left, what happens. If we do an analysis from right to left, okay, so we do analysis from right to left, okay. So our geometric datum still stays, right? So this is our x, okay. Now we will analyze from right to left. So our structure now, I'm trying to look for my cursor and I can't find my cursor. I found it. Okay. So now this is our analysis direction. Okay. When we do from right to left, right, the shear force will be going up, the bending moment will go in a clockwise direction. So this is what we call, both of them, okay, it's what we call positive shear and positive moment assumption. Okay, so that is where I drew this coming down and going in the anti-clockwise direction for the moment, because my analysis direction is from left to right. Okay, so now you see why I drew those arrows there. Okay, so now I'm going to take this whole thing again. I'm going to bring it down here. Okay, and I'm going to put here, pardon me, I'm sorry. Okay, and I'm going to get rid of this. Right. So from here, we are going to carry out static analysis. Okay, positive is going up, summation of forces in the y direction is equal to 0. So you can see over here is P/2 minus V as a function of x is equal to 0. P as a function of x is equal to P/2. Equation number 1. Okay, we from our equation number 1. Then the next thing we are going to do is we are going to do summation about moment. Anti-clockwise positive, summation of moment in the z-axis at our variable point is equal to 0. Now, what does that mean? Okay, what that means is we are going to take our moment at the red dot. Can you see where my red dot is? That is where we're going to take our moment. Okay, so from here we derive that. So our moment is minus P/2. The P/2 is going to generate a clockwise minus Px/2, right? Because moment is force times perpendicular distance plus by m as a function of x is equal to 0. So we have m as a function of x is equal to Px/2. Equation number 2. Okay. Now we will now look at, so this is equation number 1, number 2. Okay. So the limits is 0x to L over 2. We are going to just do 0 to x to L over 2. Why? Because now we are going to compare, right? We are going to compare from 0 to L over 2 for a cantilever beam now. Okay. So now I'm going to derive, okay, a cantilever beam now. So I'm going to draw a line. I'm going to draw a line over here. Right? So we are going to look at the cantilever beam. So cantilever beam, we're going to derive 0 x L over 2. Okay? So from here, we're going to draw This is our P/2. This is our distance x, right? V as a function of x, we are making an assumption of positive shear and positive bending moment. So next,